large-scale structure statistics beyond the 2-point function session. So if you wanted to go somewhere else, then now you can still leave. Okay, so all right, so I think there were many talks in this conference by lots of people who were basically discussing a lot of things that we can do beyond the power spectrum, and maybe it's just worth chatting about all of them or comparing them. So I have a very, very brief introduction. This will be probably old news for most of you, but will be over in a few minutes. Okay, so how do we analyze CMB data? Well, we are very lucky because the CMB is almost a Gaussian random field. And that means that basically this picture on the left and the picture on the right have exactly the same information content. So the field is completely determined by its 2-point statistics by the power spectrum that I show here. Okay, and that makes, of course, the analysis quite simple, conceptually at least, because we measure the 2-point function and that's it, basically, right? Yes, Ben, no, you're completely right? So if the field is non-Gaussian, then this is not true. And the real field is, of course, slightly non-Gaussian just because of secondary anisotropies. But yeah, this is at least the simple story, right? Okay, but what happens if you look at the universe a bit later? Then it looks a bit like this picture here on the left. And what I did there is so this is from the Millennium simulation. And I just took the power spectrum from the simulation and generated a Gaussian random field using the same power spectrum. So both pictures have exactly the same power spectrum, but they look very different. And the reason, of course, is that the large-scale structure today is not a Gaussian random field. So we see a lot of structure there. And that means, of course, if we only measure the 2-point function, there's lots of information that we are missing. And we want to use it somehow. Okay, I guess that's why we're here. All right, so there are very many ways how things can be non-Gaussian. So some would say infinite, but okay, so there are also very many ways how you can try to measure this non-Gaussianity of the evolved field. So this is a very incomplete list. Maybe we can even add some points if you want to add more methods. Also, the sorting is not very rigorous. Okay, so all of these methods here you can use to get information that's not in the power spectrum alone. Okay, so I started with these perturbation theory inspired models. I mean, again, like the categories are not really that clean often, but okay, so the first thing you can try to do, if the 2-point function doesn't have all the information, let's go to the 3-point function. Let's measure the bias spectrum, or the 4-point function, whatever, right? So the whole hierarchy basically of endpoint functions, and they should contain basically then all of the information of the field. You can do similar things like just measure different moments of the distribution. You can go to the just the integrated 1D PDF. And that also contains then integrated information about the whole endpoint hierarchy. The advantage of these methods is that, at least in principle, you can write down how to compute an endpoint function in perturbation theory. In praxis, or yeah, it just turns out that it's very difficult to do, because perturbation theory is not very accurate at small scales, and this is exactly where these kinds of non-Gaussian features are generated. Okay, and then the next category is something that I called morphological. So this is basically just like, it's a bit like if we as people, we look at the map of the large-scale structure, then we see things, like we see clusters, we see filaments, and these morphological probes try to use this structure somehow. So cluster number counts are kind of the classic method. This is also, of course, connected to perturbation theory. Like you can try to predict the cluster number counts, of course, analytically. But okay, so you can do something like we heard about shear peaks. Those are basically just clusters in projection and a lot of noise, but it's a similar idea to just counting clusters. Then you can do something like take a correlation function, but do something nonlinear with it before you compute the correlation function. So you can clip it, you can mark it, any nonlinear transformation of the field, and then you calculate a correlation function will contain some information that's not in the correlation function or in the 2-point function to begin with. Okay, you can look at voids or at filaments or all kinds of other structures. All right. Then something that I call topological probes. So I think, so these are a bit difficult. Okay, but I think the most well-known in cosmology are these Minkowski functionals that basically, they're different. Well, so you smooth the field somehow, and for example, then you cut it somewhere, and you look how many holes there are in the field, something like this. Okay, so you probe the topology of the density field. All right, and then there are the fancy new methods. So you just look at the map somehow. Okay, so you there are various methods where you, either you take the whole information of the map as input in your analysis. So you do a pixel-wise analysis of that somehow. There are lots of methods that I just listed here. They are different in the way they are implemented, but I think they're similar in spirit. So a lot of these are simulation-based, inherently forward models, likelihood-free models. I think they all tend to go in very similar directions. Okay, and then you can go to pure machine learning, even though like machine learning as a tool, I think can play an important role in a lot of things we do. But you can also just do like classifiers. You can just feed the whole basket structure into a huge neural net and get out parameters, whatever. Like, or you can use the networks to identify structures that you should look at. So there are also lots of different flavors of this, but usually they all go beyond what's captured by the power spectrum. Yes, Marika, that's a good point. So the likelihood free is a very, very unfortunate name, I would say, because I mean, of course, there's a likelihood. It's just, I don't know. Usually, you draw from the likelihood. You don't know it, so it's All right. Okay, I think maybe it's worth now pausing on this slide for a second, and other things that you want to add somewhere.
I mean, I would, at least I don't know much about them. I heard about one or two more topological aspects, but maybe also I'm not quite sure what Betty numbers are, so maybe they're the same. These things where, for example, people take like Voronoi tessellations and look at different inversions of this, and then the eigenvalue structure of this, so that also tells you something about the connectedness and but well, I wouldn't even know how to call this, but so these are things when which also people use to try to analyze the web structure basically,
Right.
and classify also classify different types of peaks and caustics you might have, even beyond just filament and cluster and void, but even in those have subcategories depending on how they form.
Yeah. Right. I mean, yeah, there are these large-scale structure classifiers. There are also different flavors of that.
Well, there are also wavelet and starlet transforms, right? And generally, like maybe scattering transforms that are kind of, I don't know, I think in some sense, hybrid between map-based and some kind of compressed statistics in some sense.
Right. Yeah. That's true. wouldn't even know exactly where to put them, actually. Maybe that's my fault for coming up with those weird categories. Yeah, I mean, they're not clean, okay? There's a lot of overlap. But yeah, maybe map-based. Okay, right. Yeah,
I think,
so there.
Just one under perturbation theory inspired, I guess you could also consider adding a category for compressed endpoint statistics. So things like a position dependent power spectrum or a quadratic estimator that reconstructs long modes from short modes.
Right. Yeah. 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 Very good point. So they're already. Do you have more? Sorry, I tried to look at the chat, but it's difficult. Angus, yes. The Betty numbers, I think so. But to be honest, I just saw them in the title of a paper. I don't know exactly what they are. If someone else knows. Oh. So I just know that they are like usually they come from topology. So, but that's basically all I can tell you at this point.
Yeah, the only thing I know about them is from one of the projects that's happening within kids about using persistence homology, and they use the Betty numbers as at some point during that. I've seen the talk at least 3 times over the course of the last 5 years, and I still don't fully understand it, which is usually a pretty good sign that it's a very complicated and very comprehensive thing.
Yeah,
you're not alone, Angus. I feel the same.
That is excellent news.
very good. Okay.
In some sense, those are just basically the number of holes, right? And what kind of type of holes they are. So it's clearly topology, right?
Yeah. So then somehow, yeah. I mean, yeah, all of these topological classifiers should be related somehow, yeah.
Just a question, since we're on that topic of topological probes or quantitative properties, which maybe there is no expert here, but does anyone know like how well do we have cosmological prediction or like predictions given a cosmological model on those which we could actually test? I mean, I don't really have a good feeling for like connection between parameters and models to these topological quantities.
Well, for Minkowski functionals, you can make some kind of Gaussian field predictions. I think aside from this, it's pretty hard.
Okay.
I think mostly they just use simulations to get an idea of what it should look like, right? And that's pretty much it.
Yeah. This is something that we are definitely going to talk about in a minute, I think. But yeah, not all of these quantities are easy to calculate. So for lots of those, calculating them is very, very difficult, or it's only like we only have analytic approaches in the Gaussian case, and that's where they are not interesting, of course. So this is very tricky. Yes, Arthur, there was a very good question. Sorry for that. I should have explained this more. So likelihood-free methods. Yeah, so they are, it's a poorly chosen name, I think. The idea is that you don't know exactly the likelihood, but you can sample from it. So for example, with a simulation, right? Like if you think about, you keep simulating your data until the simulation looks close to your data. Okay, something like that. And then you never use the likelihood in that sense, right? But you sampled from it and then you compared. Yeah.
I like to think of it in the terms of that you personally are free of having to specify a likelihood. that's pretty much the way in which I think of it. But I agree, it's a unnecessarily complicated name.
Yeah, poor branding, I would say. But now we're stuck with it, I think. Okay. I like the name like forward. Yeah, forward models actually more. I think many of those actually are likelihood field methods. So you just like keep forward simulating your data, and then yeah, exactly, simulation-based inference. Those are all.
You could do simulation-based inference based on summary statistics, right?
Yes.
So.
Yeah.
And you can do forward modeling without simulations or any time evolution. Forward doesn't mean necessarily in time. So it's a big term again, but okay. We have to, get some structure into it somehow.
That is true, but I think these things often are very similar.
In spirit, yeah.
Yeah. No, but yeah, those are very good points. Okay, so yeah, for a lot of these things, we don't necessarily know how to compute them.
Do you mean from the data or the prediction? Because from the data we can compute them.
We can usually measure them. Yeah.
Yeah.
But we usually like the difficulty is to get a prediction for many of those. So I think one appeal of these perturbation theory models is like, I don't know, it's very difficult in practice to use the bispectrum for inference, but at least it's conceptually clear. Right.
Stefan, before we move to how to like difficulties to compute some of them, I have like one question, which is so we know that with endpoint functions, in principle, like no matter how non-Gaussian it is, if you go to infinite endpoint, you recover all of the information from that field, right? So that's like theoretically, I think it's proven, kind of like, okay, and maybe you don't get any more information from the 40-point function, but at least you know that there's going to be like some like some, I don't know, like completeness theorem. I don't know.
Yeah, this is actually, this is a very good point that Francisco just wrote in chat. This is actually not the case, not always. There are cases where you, but I mean, that's the idea. Yeah.
Yeah, so exactly. So my question will be like, do we know if with the others we have something similar, something that, I don't know, like for example, with a wavelet, well, maybe the wavelet transforms are not a very good example, but like that, that if you get enough wavelets, then you recover all of the information from the field or things like that. I don't know. I'm just wondering.
I think,
Marcos, maybe I can answer this. Sorry, I'm a bit windy here. So yeah, there is this pathological case that I think we put. It's very well known that if you have a log normal field, you cannot expand this into the all infinite moment. So in that case, the PDF cannot be fully reproduced. And for wavelets, we have been working with one of the most expert on the field on this, which is Stefan Malat. And it's also, you cannot really claim that. So I think, I don't know, the only thing I think we will say is that with neural nets, because there is the universal approximation theorem, only in that case, probably you can claim that you can really expand this in some kind of basis that you don't know. But in general, it's super tricky, this question. Yeah. Sorry.
Okay, thank you, Francisco.
Yeah.
And I guess in some sense, I mean, the map-based approaches also all try to use the whole field as we have it. So basically, the limit of convergence, like how accurate is your model that you compare with. But it's not like a mathematically as rigorously defined expansion of anything. But in some spirit, there's also the potential to extract as information as there is.
Right.
I guess.
So you could imagine kind of a map-based, like pixel by pixel approach that works on like in a likelihood-free way, or like you have a forward model. If that becomes arbitrarily close to your data, then you also basically got the whole information out. That's, I mean, yeah. Maybe I can very briefly go to my next slightly controversial slide, because this is, I think, kind of this idea. Okay. So basically, the idea
sorry, Stefan, would you mind if I asked a quick question related to the previous discussion?
Oh, please, yes, please go ahead.
Yeah, so I'm also familiar with the statement that for a log normal field, you can't recover the full information content from the from all the endpoint functions. But I know there are experts on the call. Does anyone actually know? Suppose I have a log normal field, kind of roughly cosmological, and I measure up to the 10,000 point function. How much information is missing from that versus the full information in the field? Is there any kind of quantification? I know there's no theorem, but practically, how much information do you miss?
I guess the trouble is for that, you would need to specify what is the information there is, right?
Yeah.
I mean, it depends what you're interested in, right? Let's imagine you are interested in some quantity you will find very deeply in the tail, then the answer is you have no information about this, right? But if your question is, how well do I know the variance, then it's probably pretty well, because it's not too affected by the tails in some sense.
Okay, are there any examples which exist in the literature for things which are interesting for cosmology?
I don't know.
I mean, there are those papers about the plateau, right? You hit at some point, depending on the kind of scales you're interested in. But I guess the issue is they're always very simplistic, right? They're like, let's assume we have sigma 8 and omega m, and now I can tell you that you will extract most of the information. But I think it's very hard, especially if you want to constrain some kind of fundamental physics, extended models. I think it's very hard to answer, right?
Yeah, I guess for a specific example, you could probably do some experiment. But yeah, anyway, thanks for the discussion. Sorry to interrupt, Stefan. Yeah.
No, yeah, it was a very good point. So please, everyone, feel free to stop me. Like the more you guys ask, the better this discussion is going to be, I think. Okay. All right, yeah, so because we were talking about basically extracting the full information, I wanted to very briefly talk about this. So Cora already like complained, and I agree with her. But okay, so this is something that you will sometimes hear. Okay, so basically, we know that in the initial conditions, non-Gaussianity aside for a moment, the power spectrum contains all of the information that we can get out. In the large-scale structure, that's no longer the case. But is there a transformation that basically that goes back to the initial conditions, right? The answer is yes. I mean, this is kind of what we call an n-body simulation. So if you have the large-scale structure and you apply an inverse n-body simulation, you end up with the initial conditions that gave rise to that large-scale structure. Okay, Ben, please.
I have a question regarding Cora's comment. So why is that not true? I mean, assuming there's no primordial non-Gaussianity, we already discussed that. But if you choose the initial conditions far enough in the past, sure. I mean, if you choose your initial conditions for whatever simulation you're running at redshift of 5, then yes, you certainly have non-Gaussian initial conditions for your n-body simulation. But I mean, if you choose your initial conditions even at redshift of 100, I would expect that effectively all your almost all the information is contained in the 2-point function. Is that where am I missing a link?
I think that's not
My
quite
simple
true,
statement is you can't measure the growth function, right? With this one-to-one mapping, you need to look at different mappings at different redshifts to actually measure that. That's why I said growth of structure. I didn't claim that your initial conditions for n-body are kind of non-Gaussian.
Oh, I see. Okay. I thought there was a direct comment to okay, fine.
Yeah. Francisco, please go ahead.
Yeah, so this is very interesting, but I think this depends on scale. I think you cannot really run back an embodied simulation. I think that problem is not deterministic. Given the initial conditions, you can always produce the final condition, but I think the other way around is not always possible. I think, for instance, if you form a halo, everything there will be some kind of chaotic. So I'm not sure if you can really reconstruct this. So in that sense, going back to initial condition, I think we're going to lose this information. Whereas if we do the forward modeling, we can still extract some information there because I don't know, maybe the concentration of the halos correlates with omega matter or something like that. So yeah.
Yeah, I think Natalia, that's one for you, no?
Yeah, so if I agree with what Francisco says, and also if you try to apply this to real data, when you go backwards, you're going to amplify all the noise.
Yeah.
So in practice, I don't think that's doable with real data.
Well, but okay, so I thought that you would be more optimistic actually. No, okay, so yes, it's not a one-to-one mapping for sure, right? But you can go back probabilistically. So you can get the ensemble of all initial conditions that are consistent with your data. I mean, yeah, sure, you have a noisy process in between. Yeah,
I agree that you can get the ensemble of initial conditions that are consistent with the data, but I don't think in the backward model. So I think you have to do this forward modeling and then comparing
exactly.
to the data, but not applying a backwards transformation. Yeah. Mm-hmm.
Okay. Were there other questions? Oh, there were some hands up. Yeah, please, Francisco. Yeah.
Sorry, so also coming back, because I think I have this discussion with so many people. So I think usually the argument that they claim is that the transformation itself, from the initial conditions to, let's say, redshift 0, that transformation itself contains information. So for instance, I can take the same initial conditions and I can run 2 different embodied simulations with different omega matter or neutrinos or whatever. I will end up with 2 different fields, right? So it's not possible then that all the information at redshift 0 in these fields is contained in the initial conditions, because the initial conditions are exactly the same, whereas at redshift 0 they are not. So this mapping itself, the evolution itself of the universe, that contain information is related to what Cora said, like the growth factor and all these things. This knows about the redshift evolution. So
yeah, exactly. So Marika, I think, was next.
Yeah, I just want to ask a question. So what is the aim here? To get all the information that the universe provides us? Then in that case, what suggested here is basically the same as those map-based analysis. You have to make a lot of assumptions. You have to make a lot of assumptions to basically get that. And I think that's why, say, Cora was saying you can't get all the information because, okay, if you make an assumption for the growth of the structure, then yes, you have all the information, but maybe that's the information you want to get from the data, then you don't have it. So that's why I'm saying you have to think of what's the aim here? What do we want to get out of it before continuing?
Yeah. Robert, you also have your hand up. Is that still?
Yeah, no, it was already said. That's fine.
Okay. Yeah. Then please, Cora, and then Mark.
So yeah, I think my view of this idea was actually that you don't want to do map-based analysis, right? You basically want to apply some magic transformation to your field and then just analyze 2-point statistics because this was the input, right? In some sense. But yeah, as people already said, there might be information in the mapping, right? Especially if it's like redshift dependent. I think there's also some kind of technical question because the way we actually set initial conditions for simulations, right? We run Boltzmann solvers to redshift 0, right, with baryons and everything. And then we actually try to engineer back what kind of initial conditions we need at early redshift to reproduce this kind of linear power spectrum at large scales.
I mean, there are lots of practical problems with this kind of approach. Yeah. Marcos, please.
Yeah, so I completely agree that trying to get the initial conditions field, I mean, that will solve everything, right? But it's probably very, and I'm not only impractical, but also the problem with that if you don't know the growth, then it is, I mean, you might have different things and you won't have all of the information. But I was thinking when I saw this slide, the first thing that I was thinking was kind of okay, if you know that for example, your PDF of your field is log normal, then in principle you can define a new variable and transform that log normal to a Gaussian, right? So I thought it was gonna go I mean, towards those points more than reconstructing the initial condition field. kind of like having, okay, so you have that field, and then you try to do as many dirty tricks as you can to make it Gaussian. Is that what you were thinking too, or?
But I mean, okay, so this is the thing, no? Like, if the ultimate way to make it Gaussian is to go back to the initial conditions, you can't be better than that, right? Hubert.
Yeah, to what said. I mean, in principle, in this idea sense, as you just phrased it, this is not really, it's not making the problem simpler, it's just shifting the problem to, you would assume we would have perfect information, no noise whatsoever. It just shifts the problem to finding the precise form of G, G inverse, which is in itself, I mean, it's a shifting of problemless problemality. But yeah, and then on top, as already was said, I mean, it's not invertible, just alone due to noise and possible chaoticness, but yeah.
Yeah. Okay, Cora.
And I guess there's information in the mapping too, right? Especially if you're interested in modified gravity, assuming that G contains all of the non-linearity, right? This is what you actually want to test gravity in cosmological scale.
That's part of information, and it's still like trying to correct G, and there it contains all this information as well, even if now the intermission conditions are simple.
Yeah, Marcos, also about this?
No, sorry, I forgot to lower my hand.
No worries. Yeah. No, I think this is exactly the okay. I think this is a very appealing idea. Okay, but yeah, as you said, like Marika also mentioned this, no, like this assumes kind of that puts all the weight on your forward model. Like that has to be like precisely on point. So for example, if you're looking for modified gravity, you can, then you have to run modified gravity simulations as your model, or to undo the analysis. You could probably, like, you could do like a full parameter exploration, like then we have to ask Natalia if that's possible. But if you add modified gravity parameters to your forward model, and you also vary them, basically.
I think this is a problem with all of these beyond 2-point statistics, that you have to trust your simulation or your modeling. And that's why a lot of people prefer to just use 2-point, because you can't understand it.
Yeah.
So it's not just a problem with this method that you were suggesting. All of them have this problem, basically, to some extent.
Yeah. Yeah, I think that's, those are now we get really to the challenges. And I think those are, for most of these methods that we discussed 2 slides ago, those apply. Okay, so yeah, a lot of them we can't calculate. Actually, most of them, not really. That means that we have to either calibrate our analytical models on simulations, or we just use simulations alone. And that then leads to the question, are these simulations actually accurate enough? That's really problematic, especially once you go to something like galaxy bias or so. Like that's in some, like, well, we don't know how to simulate that. And are they fast enough? And then there's a trade-off between those two. Like our fast simulations are usually less accurate. Yeah, and that's, I mean, that, of course, that's the reason why people do analysis with 2-point probes. So I don't know, like if we go through the list, I think we need simulation input for all of those. But then this is of course always the case, right? Like if you could make this point that if you can't trust your simulations, well, then you can't do your traditional 2-point analysis either, because that's also, or that also requires simulations to actually test the analysis pipeline. Okay, Cora and then Marika.
Well, I think there's a difference, right, between kind of testing compatibility of like theory and your simulation and using the entire simulations for inference, right? And you can check scales and check different simulations. So I think I would disagree with this.
There's a spectrum. but yeah, no, Marika, maybe you go first.
I agree with Cora, and I will add that as we make the observable more complicated, it becomes more difficult to know what scales or what effects are contributing to it. And then it becomes harder to know whether your simulation is trustworthy for those effects that are going into this observable. So that's another reason that we can use two-point functions, because we have some analytic predictions for them, and then we can compare those with simulations. We know that there's this box size, this subgrid physics, so we know what kind of levels the effects are. But when you go to something like topological measurements, it becomes more complicated how things connect with each other.
Yeah. Cora, directly to that.
Well, I actually had a question. So I was wondering, let's all forget that there was the CMB, right? Let's assume we all have amnesia and we get presented with a map of the large scale structure and given the task, analyze this information. And the question is, would we actually start doing 2-point statistics if we wouldn't have been primed by the CMB that this is what works best? So maybe we're a bit biased, right? Because we had a hammer and then everything was a nail, large scale structure was a nail, lots of other things are nails.
Yeah. I wondered the same a couple of times. I think we would look at correlation functions. Like that makes sense. But Marika, how would you do it?
Well, if we look at very large scales, we see that it's homogeneous. So we might still look at these 2-point functions and so on. But I understand what you're saying, because we see this nice structure and filaments and everything. So maybe then you would think, okay, maybe categorizing based on structure type or something like that would be more natural. And this is something some people have done, but again, it's more difficult to do.
Yeah, no, we would definitely do cluster number counts. That's that's the thing. Yeah. Yeah. Okay, so one more thing that I wanted to say about this simulation issue. Like I completely agree. Like it's not a binary thing. It's not that our simulations are either completely wrong or they're completely accurate. Like they are accurate on some scales. And depending on the probe, it's easier to disentangle the scales. Right. So the question is basically, so we all know that on some scales our simulation will be wrong. But how does this propagate to the thing we are interested in? And for some of these probes, it can be very difficult to actually estimate that because they couple scales in very weird ways. Right. Okay. Yeah, the other thing is like, it's somehow connected to this issue of computability. So for many of those, we can't really compute them, or if we have to measure them in simulations. That means that the covariance is also a nightmare, because then you also have to measure the covariance in simulations, because usually you don't want to replace the 2-point analysis with your fancy new method. I mean, few people want to do that, unless you go like to the complete, maybe map-based approaches. But if you want to add information to your 2-point statistics, then you need a covariance, and that can be very difficult for a lot of these probes. Yeah, Marika?
Yeah, okay. For the covariance, I guess you'll use simulations again, but you need to have lots of simulations and you have to trust them again. But I have a question for people, especially because there are people here that use these other methods, especially like map-based or like, I don't know, machine learning and so on. My question is, what do you learn by doing that? Can you learn something other than just say cosmological parameters about the field or about the universe using this kind of methods? Or do you you're kind of like blind to what's going on and you just go from the start to the end and then say, okay, these are the parameters?
Yeah, Natalia, maybe respond to that.
Mm-hmm. Yeah, so I don't know, with work, for example, we recover the density field. So we have the initial conditions and the final or the evolved density field and the cosmological parameters. So we can use this density field for many applications. So we can use it to do a cosmic web analysis. We can do correlation with galaxies, for example, to study how they correlate with their environment, or we can use the initial conditions to run forward simulations and say, for example, if you are interested in looking at filaments, where on the sky you can find a filament, because if you trust the initial conditions that we reconstruct, you have the coordinates of these objects on the sky. So there is a lot of things you can do with this kind of methods that are not only just recovering or inferring the cosmology.
So this basically gives you a cross-check for your model, so you can make the map, make a prediction, and then go to the sky and see if that matches what you see. Yeah, it's pretty cool.
How accurate do you expect that to be? Sorry, I didn't raise my hand.
Okay. Angus, you're first, and then Cora.
So how accurate what the
I'm just wondering if you feel like you would be able to put filament finders out of a job.
Yeah, we think so. Yeah. So so Jens Jasche and Guillaume Lavaux have made a reconstruction using the SDS data, and they have made a filament catalog. Yeah.
And I mean, is it good? Is it bad?
I mean, they can recover structures that are known from other observations without having put this into the model. So for example, with the coma cluster, they can recover the formation history of the coma cluster from the inference method, and they get the coma cluster at the right position, also with many other clusters, but they get it at the right position with a mass profile that agrees with the observations. And the structure formation history that they get is also consistent with what other people have.
That's a huge boon for people who are doing cluster searches, right? I mean, that's essentially an informative prior on whether or not to believe their cluster finder. I mean, yeah, that's huge. It's very cool.
Cora? Go ahead.
So yeah, I was wondering regarding this map-based inference. One question I had, how good do you expect the kind of scale-dependent information you get out there? So I'm thinking of features you could maybe find more easily if you smooth the density field at different scales and then compare this. So is there like any way how you can estimate it, whether you are sensitive to things like this? So let's say you have kind of a very fine grid. Can you actually get the coarse features easily, or is that harder to get those?
So I think that once you have the density samples, you can of course smooth it, and you would get the structures at the scale that you want.
Sure, but you have to smooth it by hand, right? I would kind of expect if I give a finely pixelized density field, right, it should tell me that I could have smoothed it, right, and gotten this.
Okay, I'm not sure if I understand the question. So you want to do the smoothing once you have the samples, or previous, or during the inference process?
I don't want to smooth. I want to give the map, right, giving basically all of the information, and I want whatever inference to basically realize that, if you smooth on a certain scale, there's this kind of interesting feature in there, right? And I was just wondering, can you somehow estimate whether this is doable? But maybe Paco has a good idea.
Yeah, maybe I can try to answer. So I think the answer is yes, Cora. So for instance, if you go to very, very small scales, something that you want to avoid is these astrophysical effects, right? Because we don't really understand them, so you want to marginalize over all these things. So usually a neural net, for instance, will basically smooth the field in the most, I would say, trivial case. So basically, these kind of things will basically smooth things such as your filament or your cluster or whatever is there. You get this without all this contamination. So I think, yeah, the answer is yes. You don't have to worry about this. The neural net will do for you.
But only if I have messy astrophysics? What if I just had gravity?
I believe if you have gravity, there will be more information as you go to smaller and smaller scales. So then I believe the neural net will not do that because it will not have any reason to do that. I believe. There will be more modes on smaller scales.
One thing we touched already a couple of times is that these analyses often are, let's call them extremely model dependent. Okay, so we can, for example, we can focus on getting the most accurate constraints of the lambda CDM parameters. And then we calibrate everything to a bunch of simulations. But it's very, very difficult to change this to constraining modified gravity models because that requires basically running a suite of n-body simulations with modified gravity in it. And then we have the problem that we don't have really one model where we think that it's a good model. And then, I don't know, we run lots of n-body simulations with lots of different modified gravity models. It becomes very, very difficult very soon if we want to step outside of the lambda CDM framework. Robert?
Yeah, just basically jumping on that point, I agree. I was wondering, or maybe a different aspect or a slightly rephrased aspect of this. If I do map-based forward modeling inference, would there be good ways to see in the results that maybe my model is insufficient in some regard? I mean, this is a generally hard problem. It doesn't only apply to this method, but since we're talking about this now, it'd be interesting to dive into that maybe if there's some opinions on that.
Yeah, Francesco, do you want to say something about that?
Yeah, so this is a very good question, Stephen. So this is kind of similar to maybe a discussion that we have for FNL the other day. I believe that, you know, if we stick to lambda Coulthard matter, right? I mean, what about if, I don't know, I mean, there is something else that we haven't considered. So I think in principle, one can train this kind of neural nets to basically, you know, more a classifier. Is my model lambda Coulthard matter or is not? So you can imagine running a lot of these modified gravity or I don't know, things with FNL, something like that, and just train a classifier. Is that, I'm really able to explain the data from observation just using this model or not? And these kind of things basically will look for all the features or all the summary statistics where you will really see some clear difference. So this will be a way to discriminate if we really need to go beyond lambda CDM in a very generic case. I don't know how generic this could be. Another thing is looking for anomaly detection, looking for anomalies. When you have your best simulation that you can always try to look for some anomalies. If try to see the distance in some higher dimensions is very large with respect to our simulation and the real data. And if it's like that, it might be new physics, but you know, it might be also systematics. That is something that it worried me much more than maybe new physics. That is how we are really accounting for systematic effects in the forward modeling. So
yeah, I think, I mean, the straightforward question about that is then, since we're not able to really simulate to arbitrary precision, like could it just be that the classifier, for example, picks up that we are using the wrong baryonic physics model or something like that, right? Like it becomes very tricky. Yeah, but Cora?
Yeah, a similar question I had regarding kind of additional physics, like primordial Gaussianity, modified gravity. So I think what I'm worried about, we basically said, well, simulations are expensive, right? So we might have a few modified gravity models. And one thing I'm particularly worried about, you really need to be careful how you fix the other parameters. So I have never worked on modified gravity before I started looking into PDF stuff, right? And people show you this standard gravity, modified gravity, the PDF looks radically different. And if you actually dig into this with a theory model, you will see the main difference you see there is that you have some kind of different variance that is like sigma 8-like. So when actually doing your analysis, you kind of want to say, let's fix the sigma 8. And suddenly those signatures look radically different. And I'm worried that unless we have super tuned simulations, right, that take this into account, I'm not sure this can be learned by anything, right? Because basically you couldn't pick it out even with a good theory.
Yeah, I think that's really often the case. Like, yeah, often these, yeah, you see these plots, like if you add modified gravity, you get way more clusters. But then, yeah, I mean, lower sigma 8 accordingly, and they're gone. These degeneracies are problematic. Yeah, Robert?
Yeah, maybe just two suggestions regarding trying to find these things. One still back to maybe, especially for something like a simulation-based forward modeling approach. And of course, of course, you will have some estimates of the agreement, basically, or of the how well this actually, I mean, like a chi-square, but of course not quite as simple, of how well your final ensemble of forward model realizations agrees with observations. Of course, one thing you can always do that's very efficient, but then take the final simulations, for example, and do comparisons for, let's say, more physically well intuitively understood summary statistics, anything, and do comparisons in addition as cross-checks with observations, looking for anything that might spike out. But it's also a laborious process, and certain that you find the deviation, because obviously we have trouble enough with these standard methods to find these deviations from lambda CDM. So the other thing is, I want to mention, like, of course, also number of works on different types of consistency relations that you can try to check observation, or maybe forward model inference, like where you have put assumptions, for example, on assumption that the initial conditions are Gaussian and you have standard lambda CDM gravity, you expect certain relations between correlation, like power spectra and squeezed pi spectra and things like this. I'm not sure, of course, how well these hold up as soon as you get again into like a messy small scale baronic physics and stuff like that, and how you make sure it's really only valid for lambda CDM. It's maybe a bit much to ask, but that could be one approach to look for deviations.
Yeah, Marika?
Yeah, what I wanted to say is maybe slightly related to what Robert was saying. So if your aim is to find deviations from lambda CDM, and then you want to do this with like some sort of statistical method, like, I don't know, Bayes ratio or whatever else that you're doing. So some model selection statistics. Then you have to worry about something else as well. And that is, say, just using power spectrum, okay? Say your modified model power spectrum looks exactly like lambda CDM, aside from like a low bump somewhere. Now, if you take your full power spectrum, all scales, and then do your analysis, and then try to use one of these statistical methods to choose between lambda CDM and your modified model, even if your modified model was the true model, you won't get very much basically evidence for it, because you put everything in together. And because the rest of them match, this low bump is not going to be very significant. While if you know that your model has this difference at certain scale, it's better to just look at that certain scale. And I think that's why some people like to look at voids, for example, when they're looking at modified gravity, because there is something very clear there. Well, if you put everything together, you might not find it with this kind of statistical methods.
Yeah. Okay, Angus, I think, was first, and then Francisco.
Yeah, I mean, I guess it depends how you're going about that model selection, Marika, because I mean, formally on the Jeffrey scale, if your posterior if you have more posterior evidence in your new model, agnostic of whether or not it is 1.01 or 1,000, you take that model. right? So as long as the new model gives you a stronger posterior evidence, then you should take that model, even if it is only a very, very minor improvement.
There's always noise on these statistics, right? So you can't just say, if it's a tiny bit better, I'm going to take it, because that might just be the noise in your data.
Yeah,
totally. But formally speaking, like this is what the posterior evidence is telling you. The posterior evidence is telling you that this model is preferential, and therefore, if you're doing things in a fully Bayesian framework and you trust your priors and all that sort of nonsense, then, which I think is fairly apparent that we do not, I should say, then formally there's no a priori reason that you shouldn't be able to say, well, I expect the change to be small, and the fact that I see any preference means that this model is valid.
Well, I don't think you can say that, because we know that there is an intrinsic error, say on Bayes ratio or whatever you're using, and that's just the data noise realization. And if the difference between the two evidences is within that error, then it could be just noise realization. You can't say anything, basically. And the more data you put in that is not differentiable between the two models, the smaller this difference gets. That was the point I was trying to make.
Yeah, no, you're totally right. Yeah. There's also a good reason to narrow in on the point that you're interested in, which is just, you minimize the volume in which you're looking for models, and that minimizes the look elsewhere effect. So if you have a prior belief that the model should be differential in that particular region, then you should look in just that particular region to minimize the look elsewhere effect. Yeah, that's a really good point.
I think this is the problem with these model comparisons, because I mean, yeah, like in the end we are all comparing priors. That's what we're really doing. Like you can say that, I don't know, the Jeffrey scale prefers this model over the other model, but then yeah, like exactly like you two said now, right? If I want to distinguish these models and I have a reason to believe in this modified model, then I focus on the region where the difference is largest. But in a sense, that's what you shouldn't do, or should you, like, right? Like then you're basically comparing your prior on where you should look, and then it doesn't tell you anything, I think. So, I think unless the evidence for another model is very, very strong, you will not convince people in general. But yeah, Angus, please, if you disagree with that.
I think that the important aspect is whether or not you make that decision a priori or not. Right? Whether or not you say, I have a theory that tells me that there should be a difference in this particular part of the model space, and I'm going to analyze that, and I'm only going to look there, right? Otherwise, you start having to fold in, multiple comparison modifications and stuff like that. I think that's totally fair. But then, of course, you also have to do these analyses, in a sense, at least blinded. Right, because you run into the old, theta plus pentaquark conundrum, right? Where the exotic baryon was detected in 10 different surveys at 8+ sigma, just from confirmation bias. And so this is, it becomes, when you're doing this sort of stuff, especially with ever increasing numbers of hypotheses, it becomes really important that you do these analyses somewhat blinded.
Yeah, no, I completely agree with that. Yeah. All right. Okay, so we also reached the hour. So maybe this is a good place to actually wrap it up. But yeah, I think this was very interesting. So I'm not sure what do we take away from this. It's difficult. Maybe one, just to close, one thing that I keep thinking about, and I don't know the answer, but if you want to extend your 2-point statistics with some of these probes that we listed here, then is there a correct answer what you should choose? Okay, usually not, right? Like it depends on a lot of things, on your survey, on whatever you're observing. But what I mean is that if you add 2-point okay, let's say you have 2-point statistics plus cluster counts. Does adding information from shear peaks do much? I mean, apart from different systematics, but information-wise, I'm not so sure. Yeah. Okay, Robert, I started this point, so now I have to give people the chance to respond. That's not fair otherwise. Yeah. Please go ahead.
I agree.
Then it's it. That's it. Yeah.
I think this is exactly the kind of thing where these like by the talk by Louisa, is these ways of using neural nets and similar methods to try basically to quantify information contact for a certain specified problem could be quite useful. I'm not sure how feasible it be to apply them to all of this, but it could be a way to basically get at least very well objective, let's say, estimates on the information content. Not necessarily unbiased, but hopefully objective.
Yeah. I think it would be super interesting to kind of compare some of these methods, and then you somehow have to think about like how to compare them on equal footing, because that's not straightforward. But like for a given mock survey or something, like, I don't know, something to think about.
Exactly, it depends on the survey probably, which one you can do and which one would work and which one doesn't.
Yeah.
So for example, if your survey doesn't have shapes, you can't do shear peaks. So that's you.
Yeah. Right. All right. Okay. Then, now let's wrap the session up here. Thanks a lot, everyone, for your questions, for your contributions. That was really good.